This video will cover finding equations for lines. Please don't forget to click on the like button, subscribe to our channel, and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. In two-dimensional space, the slope-intercept form is commonly used as the equation of a line. To write an equation for a line, we must know 2 points on the line, or we must know the direction of the line and at least 1 point through which the line passes. In the slope-intercept form, m represents the slope and k represents the y-intercept. Observe the diagram below. The line passing through points A and B can be represented by the equation in the slope-intercept form. The slope is minus a divided by b, and the y-intercept is the value of a. It's important to note that any line parallel to the original line has the same slope and y-intercept. Therefore, it can also be described by the same equation. In three-dimensional space, two distinct parallel lines determine a unique plane. Hence, this equation represents a plane. As we can see, this equation works well in two-dimensional space, but it does not provide a complete definition of the equation of a line in three-dimensional space. Although there's an important difference in the way lines are described in 2 and 3 dimensions, the basic vector concepts in both are essentially similar. Every line can be determined by a point on the line and a direction. This principle applies to both two-dimensional and three-dimensional space. In two-dimensional space, the slope is used to determine the direction of a line. In three-dimensional space, it is more convenient to use vectors to determine the direction of a line. If we have a point P and a vector v, we can write an equation for the line that passes through P and is parallel to v. It should be noted that there exists only one such line. After careful observation, it is evident that for every point Q situated on the line, there exists a vector PQ that runs parallel to vector V. This means that the vector PQ is a scalar multiple of the vector V, and we can write PQ equals vector V times t, where t is a scalar. By utilizing vector operations, we can express this equation in a new form. Suppose that r sub 0 and r represent the position vectors of points P and Q respectively. We can apply the triangle law for vector addition to rephrase this equation in a more concise form. This equation is the vector equation of a line. Each value of the parameter t corresponds to a specific position vector r on the line. We can also write the vector equation of a line in component form. Two vectors are equal if and only if corresponding components are equal. By equating corresponding components, we can obtain three scalar equations, and these equations are called the parametric equations of a line in space. Another way of describing a line in space is to eliminate the parameter t from these equations. If a, b, and c are all non-zero, we can also solve each equation for t, equate the results, and derive the symmetric equations of the line. We now summarize the results in the following theorem. Equations of a line. A line L parallel to vector v and passing through point P can be described by the equations: vector equation of a line, parametric equations of a line, symmetric equations of the line. I will now show you how to solve common problems involving equations of lines in three-dimensional space. Find the vector parametric and symmetric equations of the line passing through point P with direction vector v. To solve this question, we need two things to find the equation of a line: a point on the line and the direction of the line. The direction is given by the direction of the vector v, and the point P can be associated with the position vector sub 0. So the vector equation is given as follows. The parametric equations are: the symmetric equations are Let's see another example. First, we use the given points to find the direction vector of the line. Subtracting the coordinates of the 2 points gives the direction vector, which is: we can either set P or Q as the position vector r sub 0. So the vector equation is given as follows. The parametric equations are: we should be careful to write the symmetric equations because c equals 0. So we write the equation z equals 4 separately, instead of making the mistake of dividing by 0 in the symmetric equation. Let's see another example. We need a point on the line, and the point on the line has coordinates 5, -6, and 7. To find the direction vector of the given line, we simply read the coefficients of t in each given component. We now write the vector equation of the line. Let's see another example. To ensure that the line passing through point P is perpendicular to the line represented by vector r, it is necessary for it to be orthogonal to the direction vector v. To achieve this, we can select a point C on the given line such that line CP is at a right angle to the direction vector v. To determine the coordinates of any point on the given line, we can use vector r, which represents the coordinates of any point on the line, such as point C with coordinates a, b, and c. Therefore, the coordinates of point C must be provided by the equation of the line. We subtract the coordinates to obtain the vector CP perpendicular to the vector R. We know that the dot product of two perpendicular vectors is 0. To find the coordinates of point C, we perform the dot product between vectors V and CP to obtain the scalar T. Similarly, we can find the equation of the line CP by following the same method as in the previous examples when given 2 points. Let's see another example. At first glance, this question may seem more difficult than the previous one, but it's actually not. The line that is requested is perpendicular to two lines, L1 and L2, and as a result, it is also perpendicular to their respective direction vectors, v1 and v2. Therefore, the direction vector of the line we are being asked for can be obtained by taking the cross product of v1 and v2. So we obtain the direction vectors directly from the symmetric equations. The cross product of v1 and v2 is given as follows. We now write the equation of the line. In order to keep the video concise, I will conclude here. However, I would like to mention that the upcoming video will cover crucial topics, including the distance between a point and a straight line, the equation of a straight line segment, and the relationships between straight lines. See you later.